Hey, welcome back to class 2. And if you're watching online, the first class, because last time sound didn't record, but this time I'm sure it will. Cool. So maybe both because this is the first recorded lecture and, in the first class, people were sort of still deciding which classes to register for. So I think not everyone in the room was here last time. And also because we sort of rushed through some of the technical material last time after the initial rah portion of the course. Let me start by briefly reviewing the model and the algorithm we studied last time. This was sort of like the warm-up. And what we're going to see is that we're sort of going to smoothly transition from this sort of relative toy model we were talking about and this sort of algorithm that had relatively toy guarantees for which we needed to make significant assumptions into sort of a real algorithm that'll be a workhorse for a large part of this class. So just to sort of recap maybe the setting that we were sort of studying and that I've asserted so far without too much evidence, but we'll get there. What I've asserted is a useful learning paradigm for thinking about learning not in well-behaved settings when there are distributions, but learning in sort of sequential adversarial settings, like you might be if you were playing a game. Okay, so the simplest variant of this problem is sometimes called learning from expert advice. But really, it's sort of a learning algorithm or a learning setting in which what your goal is to choose actions every day without knowing what the future will hold, so that in hindsight, you have the guarantee that your performance was reasonable according to a benchmark that we're going to have to talk about. Okay, so like briefly, the setting we defined last time involves a learner sort of playing in an interaction against an adversary. So the learner has K actions. We'll generalize this later in the class, but for now, think about the learner as having K discrete actions they can take. And they get to randomize. They get to flip coins. So every day, what the learner can do is they can choose a distribution over those actions. That's what this object PT is. It's a distribution over actions. And after the learner does that with full knowledge of what the learner has done, what the adversary does is chooses a vector of costs. In the end, the learner is going to take one of these actions and will experience some cost, and that cost is chosen at this moment by the adversary. Okay, so what happens is the learner chooses an action at random from this distribution on actions that he's committed to, and experiences the cost, which is the cost corresponding to that action, which is just like for action I, it's like the number in the ith coordinate of this vector of costs the adversary has chosen. And so we can talk about the learner's expected cost. Every round, the learner has some expected cost. And this interaction proceeds. Okay, the adversary at this point regroups, the learner regroups, the learner chooses a new distribution over actions, the adversary chooses a new loss vector. And this goes on for T rounds. And over the course of this interaction, the learner accumulates loss, right? Like the learner experiences some cost every round, and it adds up over all of the rounds. We'll sort of, I'll write sort of capital C, sublearner soup, capital T, to just refer to the accumulated loss that the learner has over these capital T rounds. And our interest is going to be in comparing the performance of the learner to the performance of various simple, or starting out simple, maybe increasingly complicated benchmark policies that the learner might have wished they had engaged in hindsight. And maybe the simplest such policy is just to play the same fixed action every single day. Like if I play rock, paper, scissors with you repeatedly, maybe I can like look back and think to myself, well, what if I had played rock every single time? Okay, and so similarly, we can write down or just keep track of the accumulated cost that any fixed action, like action I, would have experienced. And our initial hope will be that the cost of the learner shouldn't ever exceed the cost of this best fixed action by too much. Is there a question? Yeah.
So shouldn't that inner product be equal to the expected cost? So isn't it equal to the cost?
Yeah, so let's see. Let me first see if this question is about my sloppy the expectation is equal to this inner product. Yeah, good. Yeah, that's a good category of question. If I can answer questions by drawing squiggles on the board, that's good. Any other squiggles that would be useful for me to draw? Okay. So, the way we decided to talk about performance, at least initially, was regret to the best fixed action. And we said, okay, well, the regret over a transcript of interaction between the learner and the adversary, which we denoted by pi, and the learner's regret to some fixed action I, well, it's just the difference between the accumulated loss of the learner and counterfactually the loss they would have accumulated had they done something really simple, like played action I every single day. And our initial goal for a learner was one that would have the promise that, no matter what the adversary was doing, even if the adversary was, really just trying to screw over the learner, that the learner could promise that their regret to every single action simultaneously, that the action to which they have maximum regret should be bounded, hopefully by something small. Okay, that was the goal. Now, last time we sort of discussed this a little bit, and I think it wasn't immediately clear whether this guarantee was too weak or too strong. Like on the one hand, it seems weak. I mean, we're only comparing ourselves to really naive strategies that sort of play like a single fixed action. On the other hand, it's kind of strong because although we're comparing ourselves to these naive strategies that can't change what they're doing, these strategies can look into the future, right? We're comparing ourselves to whatever turns out to have been the best fixed strategy in hindsight, and our algorithm doesn't have to have the ability to look into the future, but these do. And you can sort of convince yourself that if we simultaneously tried to compare to complicated strategies, like strategies that could play a different action every round, and that had the ability to look into the future, that the task would be hopeless. Like suppose every day, the cost of exactly one action is going to be 1, and for the other action it's going to be 0. And I'm going to figure out which one by just flipping a coin. Well, the best policy in hindsight that can pick a different action every day gets the answer right every single day. But of course, it's impossible to predict the outcome of a coin flip more than half the time. So like, competing with the best policy period that can look into the future is impossible. Clearly, we need to give up on something, either the complexity of the policy we compete with or the ability to look into the future. And we said we'd start with giving up on the complexity of the policy, but continue endowing it with the ability to look into the future. And it's like not totally clear how you would get an algorithm that satisfies this guarantee even for simple action, simple policies like this. Okay. And so I want to write this algorithm out of the way place because I want to keep it up for a while and modify it as we go. We started last time with a warm-up case. We sort of said, okay, maybe to start thinking about this problem, we can weaken the adversary a little bit and say, the adversary has to promise us that there will be a single, that it will turn out in hindsight that one of the actions was really, really good. We don't know which one, but maybe the adversary has to guarantee that in hindsight, one of the actions was really, really good. Maybe one of the actions was perfect. Okay, so the idea was maybe there's a single action, unbeknownst to us, that in hindsight will turn out to have had zero loss the whole time. Okay, other than that, the adversary can still do whatever they want. And our initial warm-up question was, in this case, when there's a perfect action, okay, can we design a simple algorithm that gets good regret? Okay, here there's like a strategy that we can hope to undertake that wouldn't work in the general case, which is we can try to like identify which is that perfect action. Right? We can rule out actions that have ever been observed to have positive costs. Those can't be the perfect action. And we can focus our attention on everything else. That's something that wouldn't work in general, but makes sense to do if the adversary promises us there's a perfect action. Okay. So we gave an algorithm for this. We called it the halving algorithm. And it was pretty simple. And I wrote it, and I'll continue to write it in a slightly obfuscated way in terms of weights, because it's going to turn out that when writing it this way, I only have to change one line to turn it into an algorithm for the fully general case. Okay, but maybe like before I write it in this funny way, let me just tell you what the algorithm does, which is dead simple. Okay, the algorithm keeps track of which of the actions might possibly still be the perfect one. It knows there's a perfect action in hindsight. There's going to be. And so initially, it has a set of candidate actions, any of the action, containing all of the actions. Any of the actions could be the perfect action in hindsight. But as soon as it ever observes an action to have positive cost, that is proof positive that that action cannot possibly be the perfect action. Okay, so it eliminates it from consideration. Right? As soon as it observes any action to have positive cost, it just crosses it out. And what does it do with the remaining actions? Well, as far as the algorithm's concerned, they're all symmetric. They've all had zero cost the whole time. So what can it do? It's just going to play uniformly randomly across all of them. Okay, so it's like the simplest algorithm you could think of in this setting. It just, never plays things that it knows for sure are not the perfect action. And amongst everything else, it just, uniformly randomizes across all of them. Because what else can it do? Okay, so let me write it in this way. For each action, we're going to maintain a weight, initially 1. And we're going to keep track of the sum over all of the weights. Okay, initially k, because there's k actions, each of which have weight 1. And then for each time step, what we'll do is we'll play the distribution pt that just puts weight on each action. It puts probability on each action I proportional to the weight on that action. Okay, now initially all of the actions have the same weight 1. So like initially it's just playing uniformly at random across all of the actions. Then we observe the costs. And then we update the weights. And how are we going to update the weights? Well, for each action I, the weight tomorrow is equal to the weight today multiplied by an update factor, which is just, in our case, going to be 1 if the action had cost 0. We're not going to update the weight at all. And we'll multiply it by 0 if the action had positive cost, which is to say we'll just zero out the weight. Okay, so the weights here, this is why it's a little bit funny to write it this way. The weights here are not so interesting. They're either 1 or 0. We just zero them out if we ever observe the action to have positive cost. And so, and we'll do our bookkeeping to keep track of the sum of the weights. And so what the algorithm is doing at any given moment, since the weights that haven't been zeroed out yet always stay 1, it's just playing uniformly at random amongst all of the actions that haven't been eliminated by revealing themselves to be imperfect. Okay, makes sense. Okay. So let's review what we proved about this and how we proved it, because the general problem is going to have a very similar solution, both in terms of its algorithm and its proof. So I want us to have the simple case internalized. Okay, so this was the theorem. For any sequence of costs, so no matter what the adversary does over key rounds, such that there's a perfect expert, such that, in hindsight, there exists some action I star, such that every single day, the cost of that action was 0. If we look at this algorithm, the regret to the best fixed action is bounded by at most log of the number of actions, like a really good bound. We can play for as long as we want, and our regret doesn't grow at all with t, right? It grows, it's like sort of a fixed constant, and it's a small constant, right? Because log is a small function, right? So every time we multiply the number of actions by e, we only increase the regret by 1. So you can think of this as really choosing amongst an exponentially large collection of actions and still having quite a reasonable regret bound. Okay. And the proof followed a pretty simple idea that I'll just sort of remind you of in words first, and then we'll sort of write down the form of so that we can use the same framework to handle the general case. So the idea of the proof was to sort of engage in a win-win kind of analysis, right? Like, what's the algorithm sort of trying to do? It's trying to make progress in identifying which is the best action, right? When can it make progress? Well, it can make progress when the adversary reveals that an action is imperfect by giving it positive cost. So somehow if the adversary gives a bunch of actions that the algorithm previously thought maybe could have been the perfect action, positive cost, then the algorithm will make a lot of progress towards identifying what that perfect action is. Okay, so if the adversary doesn't want the algorithm to learn quickly, it had better sort of be very conservative in revealing which are the imperfect actions. It better not very frequently give new actions positive cost. But of course, if it does that, then the algorithm is going to have low cost. It's going to have low cost and therefore low regret. And so, the high level idea of the algorithm is, or of the analysis, is that every single round, one of two things must happen, either of which is good for the algorithm. Either the algorithm makes a lot of progress towards learning, which is the perfect action, or if not, the algorithm has low cost. Okay, and in particular, what the analysis does is it sort of tightly couples these two quantities, the amount of progress made by the algorithm and the cost of the algorithm. And the way we keep track of the amount of progress made by the algorithm is by keeping track of the cumulative weight of all of the actions, which in this case is just the number of actions that haven't yet been eliminated. Okay, that was the high-level idea. And this was the low-level idea. So the thing we want to keep track of at each round is the following. Let's let CT be the set of actions that the algorithm chooses to sort of, or that the adversary chooses to reveal to the learning algorithm are imperfect. Okay, so it's like the set of actions whose cost is positive. These cannot be the perfect action by definition. Now, some of these actions the algorithm already knew were imperfect. Some of these actions maybe had positive cost in previous rounds, so it's not news to the algorithm. But for how many of them is this news to the algorithm? Well, that's the number of actions in this set that still have positive weight, still have weight 1. Okay, and so we said the weight of this set CT is the sum over all of the actions in this set of their current weights. The ones that the algorithm knew were imperfect have weight 0, and so don't contribute to this cumulative weight. And the ones that the algorithm just learned for the first time are imperfect have weight 1. So this is sort of the number of experts that the algorithm newly learned must be imperfect. And because what the algorithm is doing is it is selecting uniformly at random from the experts that it thinks might still be perfect, the probability that it picks an action that has positive cost, and therefore the expected cost of the algorithm, since the costs are at most 1, is always upper bounded by the weight of the imperfect experts at round T over the cumulative weight of all of the experts at round T. Okay. And another way of writing this same thing is that if I look at the relative decrease in weight between round T and T plus 1, this is always upper bounded by 1 minus, sorry. This is always upper bounded by 1 minus the cost of the learning algorithm at that round, because we know exactly how the weight changes between each from one round to the next, right? What the algorithm does to get the weights at the next round is it zeroes out the weight of all of the experts that it newly learned to be imperfect. Okay, so the cumulative weight tomorrow is equal to the cumulative weight today minus the weight of the experts that were revealed to be imperfect today. Okay. So, right, the key is that we can relate both the cost of the algorithm to the weight of the experts today, the weight of the imperfect experts today, and also the decrease in the cumulative weight of all of the experts. And because we can do both of those things, we know that we can bound the cost of the algorithm by the relative decrease in the weight of the experts. Okay. And so at this point, it was basically just putting together the pieces. What we're doing is we're going to keep track over time of the cumulative weight over all of the actions. Now, we know two things about this, really three things. We know that initially, the cumulative weight over all of the actions is k. Right? They all start with weight 1, and there's k of them. We know that since there's a perfect expert, there's at least one expert that never has its weight zeroed out. And so the cumulative weight never goes below 1. It starts at k. It cannot go below 1. And we know that every time the weight decreases substantially, we know that the only rounds on which we can have high loss are the rounds on which the weight decreases substantially. Okay, and so the algebra that follows is just sort of keeping track of our cumulative loss in terms of the decrease in the weight, and noting that if the weight starts at k and never goes below 1, it just can't decrease that much. Okay, so what do we know? Even at the very end of the algorithm, the cumulative weight is at least 1. There's a perfect expert. And we know exactly, we can write exactly an expression for this cumulative weight in terms of the updates. It started at k, right? Initially, the weight was k. And at each of the rounds, from day 1 through t, it decreased by some multiplicative factor, just by definition, until we had the final weight. And we can relate this multiplicative factor to the cost of the algorithm. So this is upper bounded by k times the product over all of the rounds of 1 minus the cost of the algorithm, which is at most k times the product of e to the minus the cost of the algorithm at that round, because 1 minus x is less than or equal to e to the minus x, which is just k times e to the minus cumulative cost of the algorithm. And at this point, we have an expression that on the right-hand side has the thing we want to show is small, the cumulative cost of the algorithm. On the left-hand side, we've got just a constant, 1. And just solving for the cumulative cost of the algorithm gives us the upper bound we want. Okay, so far this is sort of, so far this is all review. We did this last time, but I wanted to put this back into your working memory because this is exactly the point of departure for today. Okay, so first, any questions about the model or what we've proven? Like on the one hand, the model is quite restrictive. The adversary, in this setup really can't mislead us at all about which are the good actions. Like there has to be like baked in here, like a single good action that they've sort of planned on ahead of time. And they can never, they can never cause that action to have positive cost. On the other hand, we proved an extremely strong bound that no matter how, no matter what the adversary does over an arbitrarily long interaction, you might think the adversary might have some clever strategy for trying to mislead us, at least for a while. Our cumulative cost can never get bigger than like a fixed constant, independent of time. Okay. And so maybe like the first question as we try to move to the general case is, what might go wrong with this algorithm? If we now allow the adversary to choose arbitrary costs for the actions every round, we no longer tie the hands of the adversary, and yet still try to use this algorithm. Like, have we actually learned anything about the general case about this algorithm? Does it apply there? Or were we taking too strong advantage of the sort of special structure we assumed in this toy case? What if the adversary can pick arbitrary costs at every round, and we try to run this algorithm? What happens? Yeah, I think you're pointing at the fact that like at some point the algorithm's just going to like run out of actions. Like what the algorithm's doing is it's keeping track of these actions. It's crossing them out as soon as it observes them to do anything imperfect at all. And if we don't have this promise that the adversary is, keeping in his back pocket a perfect action, we might cross them all out. And then what do we do? Okay, so that's the worry you might have, that maybe sort of in trying to handle this toy case first as a warm-up, we have over-indexed on this special property we've assumed of the adversary that there's this perfect action. Because sort of the whole premise of this algorithm is that we're crossing out actions as soon as we learn they're imperfect. And so, the concern might be that this doesn't generalize at all. Okay. But there's something we can do, and I've sort of written the algorithm in a leading way to point to what that something is. So what do you think? Like, the general premise of the algorithm still seems pretty reasonable. Like, we're sort of keeping track of weights on the actions as a function of their past performance. And every day we're selecting an action somehow with probability proportional to its weight. So actions that historically have done better than others are more likely to be played. Actions that historically have done worse than others are less likely to be played. Okay, it seems like a reasonable thing to do. The problem is that we've been really aggressive at updating these weights. As soon as an action has been observed to have, any positive cost at all, we've slashed the weight down to 0. And so the general idea for the algorithm we're going to see in a moment, which is called multiplicative weights, is to do exactly the same thing, but just in a less aggressive fashion. We're going to try to reduce the cost, or reduce the weights on actions in proportion to their cost, but without sort of ever zeroing those weights out, because we have to leave open the possibility that in the future it might turn out that these actions that initially seemed like they were bad, that they were high cost actions, turn out over the long horizon of time to redeem themselves. We need to leave open that possibility. And okay, so like the multiplicative weights algorithm will be the following. I'm just going to change a single line here. Rather than zeroing out the weight of an action that has positive cost, what I'll do is I'll reduce the weight of that action in proportion to its cost today. Okay, so just to sort of say this out loud from the beginning. We continue to have weights for each action, all initially 1, because we don't know, initially everything's symmetric, that we have no reason to prefer one action over another. We continue every round to play each action with probability proportional to its weight. And now when we observe the costs, we take the weight from yesterday and we multiply it by some number that is smaller the higher the cost of the action. Okay, so there's like some parameter eta called the learning rate that we're gonna keep around and, you know, set optimally at the end that is controlling how aggressively we are cutting these weights. Okay, so if eta was 1, then if the cost for an action was maximal, if the cost for an action was 1, this would say, you know, we cut the weight down to 0. So we don't want to do that. That's sort of like the halving algorithm that we just analyzed, and we don't want our algorithm to run out of actions. So think of eta as something less than 1. This is going to be a less aggressive update than the halving algorithm. If the cost is 1, we're going to reduce the weight of that action by a factor of 1 minus eta. If the cost is 0, we won't reduce the weight of the action at all. And in between, we'll do something in between. Okay, that's the only change to the algorithm. And because there's no longer a perfect action, it's a little bit less clear what the algorithm is doing. Like, in the case of the halving algorithm, we could sort of think of it as some kind of binary search, basically. Like, you know, we were sort of eliminating actions when they were observed to be imperfect. We rigged things up so that whenever we had high cost, we eliminated like half of the actions. So whenever we had constant cost, we eliminated a constant fraction of the actions. And how many times can that happen? You know, log k many times. Maybe it wasn't too surprising in hindsight that this was the bound we got. Here, there's no notion anymore of like eliminating actions or searching for a perfect one. Nevertheless, the strategy for analyzing this algorithm is going to be the same. The idea is going to be to look for some kind of win-win. And in particular, we're going to continue to think about the sum of the weights as sort of a potential function that's going to mediate this win-win analysis, such that every round, one of two things has to happen. Either we have low cost that round, in which case everything is good, or we somehow make a lot of progress by eliminating a lot of weight, substantially reducing the weight. And, you know, there's something a little bit conceptually tricky that comes up here, which is a lot of progress compared to what? Right, like in the case where there was a perfect expert, we knew that there was an action here that would never have its weight go below 1. And so you just couldn't reduce the weight, the cumulative weight of the actions that many times, because the cumulative weight of all of the actions never went below 1. But now that's not the case anymore. I mean, it could be that all of the actions are really high cost every single round. And so it might be true that every time we experience high cost, we reduce the weight of the, you know, experts cumulatively by a large multiplicative factor, but that doesn't mean that it can't go on forever anymore. Like that could just go on forever. And this is sort of related to the fact that it is not possible in these adversarial settings to prove that our algorithms have low cost in any absolute sense, as it was in the special case where there was a perfect action, right? Like when there was a zero cost action, proving that the algorithm had small regret was the same as proving that it had small loss, because the best action had zero loss. Now, if all of the actions have cost 1 every round, our algorithm won't have small cost. Every policy will have cost, you know, t. But our goal is not to show that the cost of the algorithm is small in any absolute sense, but to show that it is small relative to some benchmark class of policies. Okay? And what we can do is we can relate the cumulative weight of the algorithm to the performance of the best of these benchmark policies. Right? The cumulative weight of the algorithm on all of the actions, it could get really tiny, but the only way it can do that is if the benchmark policies also have high costs. And so that's going to be the idea of the analysis. Okay. So let me first state the theorem that we're going to prove. And then, kind of pontificate a bit about its implications and then prove it. Okay, so maybe the first thing to notice is that there's still this number eta that we haven't actually assigned a number to. It's just a variable. And so any theorem we can prove at the moment is going to be in terms of this parameter eta, the learning rate, that basically controls how aggressively we're slashing weights when, for sort of actions that are underperforming. And the theorem is going to help us, decide what's the right way to set it. Okay, so let's, consider some learning rate eta, and I want it to be less than 1/2. So we're never going to slash these weights down to 0. We're always allowing them the possibility of, we're allowing each action the possibility of redemption in the future. Okay. Then for any sequence of costs, and for any action, the regret that this algorithm, the multiplicative weights algorithm, has to action I which is just the difference between the loss of the algorithm and the loss of the policy that plays action I every single round, is never more than log k over eta plus eta times the cost of the corresponding benchmark policy. Okay, so it's never more than log k over eta plus eta times what the cost you would have gotten had you just played action I every single day. Okay. Now, this is some bound in which eta shows up twice, right? There's this first term, log k over eta. The smaller you make eta, the less aggressive you make the algorithm, the bigger this is going to be, which sort of makes sense, right? Like if I never updated the weights at all, then I would never learn anything. So I can't make the learning rate too small. On the other hand, I've got this other term, eta times the cost of the benchmark policy I, that gets smaller the smaller I make eta. Okay, and so I'm going to want to pick eta to balance these two things. And how to do that depends on what I believe about how expensive these benchmark policies are going to be. Okay, so just for a sort of comparison, in this special case we analyzed in the halving algorithm, right? What was the special case, right? We said there was a perfect action. Well, that's the same as saying that we were analyzing that algorithm in the case where there was some action I whose cumulative cost, when viewed as a benchmark policy, was going to be 0. Okay. Now, if we assume nothing about the algorithm at all, if we assume nothing about the adversary at all, it could be that every single action has cost 1 every day, and so its cumulative cost is t. But suppose we know something. Suppose that we believe that there exists an action I star, our sort of analog of the perfect action, such that the cumulative cost of this action is at most b. Well, in that case, we can choose eta to balance these two terms. By setting it to be like log of k over b. And the regret that we get would be at most 2 times the square root of b times log k. Okay. So like we can start by thinking about maybe the optimistic case when we sort of believe that the regret of that one of these actions is actually good. The regret of one of these actions is small. Yeah. That's right. Yeah, you are getting ahead, but that is true. Yeah, maybe I'll mention that in a moment. Yes.
So for the Hamming algorithm, it would be 0. In theory, it means that if you 0, that's how regret scales with line like 10.
So so we can't, in the theorem, eta has to be less than 1/2. So, really, when I say, but like you can't set the learning rate parameter to infinity. So, the regret is really, it can never go below log k.
So this one only
yeah, but that's a good question. Let's compare to the Hamming algorithm. Right, the regret bound of the Hamming algorithm was log k, but it required the assumption that there was a perfect expert. Suppose we want this thing to be on the order of log k, or we can't make it smaller than log k because of this assumption that that eta is not too small. But actually, like b can be as large as log k, and this bound is still on the order of log k. Right, so right, even if b is greater than, say, or b is, say, 4 log k, which is what we need for our setting of eta to be like legit, to be less than 1/2. Then, what this gives is like a regret bound that is at most 4 log k. Okay, so it's like only a factor of 4 worse than what we got from the Hamming algorithm, but we're making a substantially weaker assumption. Right, like the Hamming algorithm, we assumed there was like a perfect expert. We no longer need to assume that to get like a log k regret bound. There just needs to be sort of like an expert that doesn't make too many mistakes. It turns out more than log k mistakes. Okay, so like we can actually get the same guarantee as the Hamming algorithm under a substantially weaker assumption. And we always know that b is at most t, right? Because the costs are bounded by 1 every round, and so the accumulated cost over t rounds can never be more than t. And so even in the worst case, at least if we set eta appropriately, we get the regret bound that's at most 2 times root t times log k. So this is a regret bound that is growing with t now. Okay, the longer we interact with the adversary, the larger our regret bound will grow. But it is growing sublinearly with t. It's growing asymptotically slower than t, which means we're learning. Because if we look at the average cost that our algorithm is incurring over time, which is going to turn out to be a relevant thing to look at in a lot of the game theoretic applications we study. The average cost over time of our algorithm is getting smaller. It's going to 0 as compared to this benchmark class. It's getting smaller at a rate of 1 over root t. Right? The average regret, the average cost per time compared to the benchmark is the regret divided by t. Okay, so this is, even in the worst case, quite a strong bound. Yeah.
So you're saying that you're often achieving this data for that. Does that work? Like, if you isn't it possible that you could, then you're choosing something that is not like perfectly calibrated with the actual performance of the bot?
Yes. So maybe this is sort of getting at Eshwar's question. So yeah, so maybe it looks like maybe I'm trying to pull a fast one here. I'm sort of saying, look, it's like the same algorithm. And if there's a really good expert, if there's an expert that makes fewer than log k mistakes, this algorithm, is no worse than the halving algorithm, which was this toy thing, because it was brittle to the expert making even one mistake, having even one high cost day. The same algorithm that can do that can get like this absolutely worst case guarantee of root t, right? But maybe I'm pulling a fast one because those two bounds came from different settings of eta, which I need to run the algorithm. Yeah, so it turns out you can sort of get both of these things simultaneously, even if you don't know upfront which of these, what's going to be the case. You can sort of compete with whatever b, this bound ends up being in hindsight. And there are, complicated things you can do that try to do this in a more elegant way. But a very simple thing you can do, which does the same thing, but maybe lacking in some elegance, is just to sort of do what's called the guess and double trick. So I could start out really optimistic. I could say, I think there's an expert out there that's not going to make more than b mistakes. For b is, I don't know, log k. And I start running my algorithm. And then at some point, my youthful optimism is extinguished because I observe that the experts suck, at least according to my expectations. They've all exceeded this mistake budget that I set out for them. So what do I do in that case? I sit and cry for a little bit, I double B, and I restart the algorithm. Okay, now I do it again. I've got new expectations appropriately lowered. I run the algorithm, maybe at some point, again, I'm disappointed. Cry for a bit, I double B, I lower my expectations, I restart the algorithm. So since I'm doubling B every time I've observed a mistake, first of all, the final bound of B I arrive at is no worse than a factor of 2, larger than what the true ex post value of B turns out to be. On the other hand, since I'm, the B can never get bigger than T, since I'm doubling B every time, the number of times I sort of am disappointed and have to restart the algorithm is at most log T. So if I'm willing to pay an additional log T factor on top of this bound to account for the times when I might have to restart the algorithm, I can compete with the best B in hindsight. Okay, and yeah, there are things that work and are more elegant than restarting the algorithm, but they can be substantially more complicated. But if you don't care about sort of extremely fine-grained bounds, then this sort of guess and double trick works. Okay, good. Yes.
Wait, sorry. How does B feed into your?
Oh, because the learning rate parameter, which is sort of used in the algorithm, it's how the weights are updated. It's set as a function of B, which, you know, I can do at the beginning if I happen to know an upper bound on B, but if I don't, I run into this difficulty that I sort of need to learn it as I go.
And so just setting B.
Well, that would work. If I could just set B equal to T at the start, and I could get this regret bound always. But this might be worse than I needed to get if it turns out, for example, that there really was a perfect action. And so if I want to get this bound, then I need to set, then I either sort of need to know a good upper bound on B ahead of time, or I need to do this guess and double thing. Good questions. Other questions? Yeah.
Do you guarantee that ln k over b to the square root is less than 1/2 somehow?
If B is at least this big. So this is why, this is why you can't sort of get impossible bounds. Like you can, this is only a legitimate setting for B larger than this. Yeah.
Then is this exact optimal thing to do like algorithm operating for minimize effect?
I guess it depends on how finely you define the exact optimal thing. That there is a long modern literature where people try to sort of refine bounds like this. So there's a sense in which these bounds are the optimal thing if what you want on the right-hand side of this inequality are sort of constants that do not depend on the sequence. But you can get better bounds that sort of, are strictly stronger than these, where the thing that shows up on the right-hand side depends on other properties of the sequence, other than just sort of the maximum cost of any action. So, if the costs are predictable in some way, if they're low variance, there are various sort of refinements to these kinds of bounds that this algorithm does not get. But this algorithm is sort of getting already up to constants the sort of optimal bounds where the thing that shows up on the right-hand side doesn't depend on the sequence.
In the worst case of that sequence, it would be better.
That's right. That's right. So like, this kind of thing is optimal if what you care about is bounds that hold in the worst case over sequences and that do not refer to the sequence, do not refer to properties of the sequence themselves. But like there's lots of interesting work on algorithms that can simultaneously get this kind of bound in the worst case, but can also promise to get sort of better bounds in the event that sort of the sequence is less than adversarial. And maybe we'll talk about some of those in this class. Yeah. Yes. Yeah. There's a big literature on trying to come up with sort of parameter-free versions of this. Maybe in the simplest case, so you're saying like even here, where I sort of say, okay, in the worst case, like the upper bound of the cumulative cost of any action is t, and so you can just set eta to be root log k over t. Like maybe you're saying even then I need to know how long this interaction is going. I need to know what capital T is. Okay, so maybe that's like the first parameter you might want to remove. Of course, you can use the doubling trick there as well. There, it turns out there's sort of a pretty simple parameter-free version of the algorithm where the learning rate eta can be parameterized by the current time step t. And you can get very similar bounds by sort of having the learning rate depend on something like 1 over the square root of the current time step rather than 1 over the square root of the time horizon. And then you don't need to know the time horizon. Yeah, and there's a big interesting literature on trying to come up with parameter-free versions of algorithms that can get sort of finer grained bounds. That's a good question. Like knowing these things ahead of time is often difficult, and these sort of guess and double tricks, while they sometimes work, are, at best inelegant and not things you'd really want to run. Good questions. Other questions? Okay. So let's think about how to prove the theorem. Okay. So at a high level, we want to replicate the form of the argument we gave when analyzing the halving algorithm. So let's just sort of remember the ingredients to that argument. We needed to know, well, first of all, what we're doing and what we're going to continue to do is we're going to analyze the evolution of the accumulated weights over all of the actions and how that changes over time. Okay, so just as before, we know that the accumulated weights start out at k. There's k actions, they each have weight 1. The second thing we need to do is we need to relate somehow the cost experienced by the algorithm at each round to the degree to which these accumulated weights decrease. In the halving algorithm, that was a relatively simple thing, what's happening in this line here. Here, we need to figure out some other way to do it. And finally, like in the halving algorithm, we knew that the weights could never go below 1. That's not the case anymore. And so we need to figure out some other way to lower bound how small the weights can be at the end of this interaction with the adversary. And the trick is going to be, rather than trying to lower bound it by some absolute constant like 1, which is no longer possible, all of the actions could be terrible. The trick will be to try to lower bound it as a function of the performance of these sort of benchmark policies we're trying to compete with. The idea will be to show that the only way the cumulative weights can become tiny is if all of the actions on their own had high cumulative cost. And therefore, if our algorithm is doing badly, that's okay according to the regret metric, because the benchmark policies are also doing badly. That's going to be the idea. Okay. So let's start by thinking about how we can relate the evolution of the cumulative weights, the decrease in weight from round t to t plus 1 to the cost of the algorithm at day t. And let's start by sort of just looking at the weight update rule. Okay. So what we're doing is we are subtracting off a fraction of each weight in proportion to the cost of that action. Okay, so if we sum over all of the weights of sort of the amount we have shaved off of that weight, it's going to be proportional to the sum of the weighted costs of those actions. Okay, so the cumulative weight at day t plus 1 is equal to the cumulative weight at day t minus the amount of weight we've removed as part of this update. How much weight have we removed? Well, eta times the sum over all of the actions of the weight of that action times the cost of that action, right? Because from each action, we remove eta times the weight of the action times the cost of the action. Now, I can write this as the weight of the algorithm at round t times 1 minus eta times the cost of the algorithm at round t. Because what's the expected cost of the algorithm? It's just right, so the algorithm is randomizing and choosing an action proportional to the weight of that action. And so it's just, well, it's the probability I choose each action times the cost I experience if I choose that action, which is just the inner product of the weights and the costs. Okay, and so this is the sort of key insight that lets us relate the cost of the algorithm at day t, this thing that we want to control, with the sum weights over all of the actions, this thing that, at least in the halving algorithm, was able to serve as a useful potential function for us. Okay, so here's sort of one of the analogs we now have for multiplicative weights that is an analog to one of the sort of driving forces behind the analysis of the halving algorithm. Now, how about the others? Now we still know, just as for the halving algorithm, that the initial weight, the initial accumulated weights is k, right? All of the weights start at 1. There's k of them. Initially, the weight starts at k. What about the final weight? For the halving algorithm, we knew this was at least 1. And what do we know here? Well, in a regret bound, we're comparing the cumulative cost of the algorithm to the cumulative cost of action I. So let's think about the weight of action I. Well, the cumulative weights, it's the sum over all of these weights. They're all non-negative. So it's definitely at least the final weight of action I, the benchmark policy to which we're ultimately comparing ourselves. Okay, the sum of the weights can't be smaller than any single weight. But we know exactly what the weights of the weight of action I is in terms of the costs of action I, because we have a particular update rule. Right, so the weight of action I, it started out as 1. And then at each round, over these t total rounds, we made it smaller by multiplying it by 1 minus eta times the cost of that action. Now, for numbers C that are between 0 and 1, which is the case for our costs, it turns out that 1 minus eta to the C is only smaller than 1 minus eta C. And so we can bound this by 1 minus eta raised to the power of the cost of action I at day t. We're still taking the product over all of the days. And now we've got like a fixed base that we're sort of multiplying with an exponent. We're multiplying these things together. What happens to exponents when we multiply them together? They add up. And so this is just 1 minus eta raised to the cumulative cost over all t of the rounds of action I. Okay. So now we can, oh, yes. WT is the sum of all of the weights. Where are we looking? From here to here?
No, that line down.
Okay. Oh, here we are. Okay, so WT times 1, that's the WT here. Yeah, and then here we're sort of recognizing that the expected cost of the algorithm at day t is the sum over all of the actions of the weight of that action, the probability we play that action, times the cost of that action. And so what we have here, oh, sorry. I skipped a step, which is maybe leading to this confusion. Let's see, so. Yeah, so like the probability, the weights are not the probabilities. The probabilities come from normalizing the weights by WT. So let's see, what's the best way for me to do this without erasing crucial stuff? Okay, so the step that I skipped is the step that moves from this to the expected cost of the algorithm. What is the expected cost of the algorithm? CTL is the sum over all of the actions of the probability of playing that action, which is the weight of that action divided by WT times the cost of that action. Okay. So without the normalizing term, this inner product, WIT dot CT, that's what shows up here. To get the cost of the algorithm, we need to multiply by the normalizing term, which is why this is also multiplied by WT over here. Yeah, sorry, that's a non-obvious step that I should have mentioned. Okay, good. Okay, so let's see. Let's summarize where we are. we want to sort of replicate this logic for the multiplicative weights algorithm. Previously, right. Previously, we knew that the cumulative weights at the end were at least 1. Now we know that the cumulative weights at the end are at least 1 minus eta raised to the cumulative cost of action I, the policy that plays action I every single day. Previously, we had sort of this simple relationship between the relative decrease in weights from day t to day t plus 1 to the cost of the algorithm experienced at day t. Now we have a very similar relationship. Previously, we knew the weights started at k. We still know the weights started at k. So we're in a good place to repeat the analysis. Okay. Starting off in the same place, we know that the sum weights over all of the actions maintained by the algorithm can never get too small, at least if there's some benchmark policy I that doesn't get too small. The only way this can get too small is for every benchmark policy I to have high cost. That's what makes the left-hand side here small. Now we still know an expression for what this looks like. The weights started at k, and then at every round, 1 through capital T, the weights were reduced by a multiplicative factor that we can understand in terms of the costs of our algorithm. Okay, so at every round, the weights are reduced by a multiplicative factor equal to 1 minus eta times the cost of the algorithm at that round. Now, 1 minus x is only smaller than e to the minus x. And so we can bound this by k times the product over all of the rounds of e to the minus eta times the cost of the algorithm at round t. And again, when we multiply exponentials, the thing in the exponent adds up. So what we get in the end is k times the exponential of minus eta times the sum over the cost for a fixed action I over all t of the rounds, which is just the cumulative cost over all t of the rounds for action I. And now, right, this is the cumulative cost over all of the rounds for the algorithm. And so now we have something of the form that we want. We've got an inequality where on one side we have the cumulative cost of the algorithm, the thing we want to show is small. And on the other side, we have the cumulative cost of any one of the benchmark policies. Okay, those were the two things we wanted to relate. And so in some sense, we're done. You know, all that remains is to solve for the variable we care about, which we do by taking the log. And what this solves to is that the cumulative cost of the algorithm is at most 1 over eta times log k plus the cumulative cost of action I times log 1 over 1 minus eta. Now, we haven't yet used the fact that eta is less than 1/2. I want to use that now to just simplify this expression a little bit. Okay, so it turns out that when eta is less than or equal to 1/2, log of 1 over 1 minus eta can be bounded by eta plus eta squared. And so the bound we get here is that the cost of the algorithm is at most log k over eta plus 1 plus eta times the cumulative cost of action I. And the thing we care about is regret. So it's the difference between the cost of the algorithm and the cost of the best benchmark policy. But if we subtract off, the cost of the best benchmark policy from the right-hand side, well, we had 1 plus eta copies of it. If we subtract it off, there's only eta copies left. So we get the bound we wanted. Okay. So essentially the same analysis as the halving algorithm, even though maybe it seemed like our design of the halving algorithm was perhaps over-indexed on the simplifying assumption we made that there was a perfect expert, so that we could sort of embark on like a binary search-like strategy. Actually, the same algorithm works in the general case. Now, maybe foreshadowing what I want to do next class, let's think about this bound and how it relates to the algorithm. Okay, so on the one hand, for both the halving algorithm and for multiplicative weights, the dependence we have on the number of actions we can consider is really good. It's logarithmic, which means that we can get pretty good learning bounds, even if our benchmark class consists of exponentially many things. Okay, and regret bounds become stronger the richer you make the benchmark class, right? Regret bounds say you're doing as well as the best thing in some benchmark class. If you make the benchmark class bigger, that just translates into better absolute bounds. So you really would like to compete with a huge number of things. And these kinds of regret bounds seem like they're going to allow it, right? Like the regret bounds get worse only logarithmically with the number of benchmarks you choose to compete with. On the other hand, running time is going to start to become an issue, right? Like these bounds scale logarithmically with the number of experts, but what the algorithm is doing is it is like explicitly maintaining a weight for each of the actions. And so if I really try to like take advantage of these regret bounds and throw in exponentially many actions, my algorithm is going to run in exponential time. And so what would really be nice is if we could get the best of both worlds, at least in some circumstances. Get regret bounds and running time bounds that scale only logarithmically with the number of actions. Then we could actually take advantage of the fact that we might be able to compete with an extremely rich class of benchmarks. And of course, we're not going to be able to do that in full generality because if we're going to have running time that doesn't scale linearly with the number of actions available to us, it must be that for most of them, we never even look at them. We never even sort of touch them. We don't have time to even point at all of them. But maybe in sort of certain cases, there's structure of the problem that we can take advantage of that gets us past this sort of unfortunate mismatch between the regret bounds, which are great. They scale only logarithmically with the number of actions, and the running time bounds, which scale linearly. Okay, so that's what we'll try to do next time. Yeah.
So the running time bounds, they scale linearly.
They scale linearly because the algorithm right, literally has to, like, first of all, update these weights every round. It's to look at the cost of each action and, somewhere like keep track of a weight for each of the actions and reduce it in proportion to the cost. Yeah. And like it's explicitly, the object it is explicitly maintaining, which is a distribution over actions. Like that object is just a vector of length equal to the number of actions. Yeah. So even just to like write this thing down takes time linear in the number of actions. If we want to do better than that, we have to figure out some way to like implicitly represent the distribution without writing it down.
Oh, okay. Because I thought that you always need a W no matter what algorithm. WT is always going to scale.
That's right. So beating this in terms of running time is going to require doing something sneaky. Like we're going to have to maintain this distribution without explicitly writing it down.